Game Theory and Learning in AI, and this chapter is Competitive Games. Pure Nash Equilibrium, and these are the topics for this lecture. Now let's do a brief recap of biometrics games. So a biometrics game has two players or agents, and each agent has a set of uh, actions, usually a finite set of actions in a biometrics game. Now for every pair of agent actions, there's a payoff, which is a numerical value for each agent. And each agent tries to maximize its payoff. Here is an example of a biometrics game. There are two players here, or agents, agent 1 and agent 2. Agent 1's actions are A, B, C, and D. These are the possible actions. And likewise, agent 2's actions are P, Q, R, S, and T. And these numbers in this table are the payoffs. So if agent 1 chooses A and agent 2 chooses P, then the reward of agent 1 is 1. It's in blue. Everything pertaining to agent 1 is in blue, and everything pertaining to agent 2 is in red. And so agent 2's payoff would be 1, 2. If agent 1 were to play B and agent 2 would play Q, then their payoffs would be 7 and 8. And this actually is the best possible combination for the two of them. The sum of the two payoffs adds up to 15, so both gain quite a bit. But Agent 1 is not aware of Agent 2's payoffs, and likewise, Agent 2 is not aware of Agent 1's payoffs. So this is Agent 1's viewpoint. Now suppose agent 2 plays Q, then agent 1 can pick A, B, C, or D, one of these four actions. And since agent 2 is playing Q, these are the possible payoffs. And naturally, agent 1, who's trying to maximize his payoff, would select action D because it would get a payoff of 8. This is agent 2's viewpoint. So if agent 1, let's suppose, were to play C, then agent 2 would be looking at these payoffs, and it would pick R because R gives the agent 2 the highest payoff. These two circled points are the Nash equilibrium points. This Nash equilibrium corresponds to agent 1 playing action C and agent 2 playing action R and receiving payoffs of 4 and 5 respectively. Now, why is this at equilibrium? Because suppose agent 1 unilaterally deviates, then it would get a payoff of 2, 1, or 3, which is less than 4. So agent 1 has no incentive to deviate from this action C. It's the same thing with agent 2. The action for agent 2 is R, and the corresponding payoff that it receives is 5. If agent 2 were to deviate, then it would get 0 if it chooses S, 1 if it chooses Q or T, and 5 if it picks P. But this is still at Nash equilibrium because agent 2 does not have any real incentive to unilaterally deviate uh, because there's no way it can receive a higher payoff. Likewise, this is also at Nash equilibrium. So we begin with the formal definition of a normal form game. A normal form game is a three-tuple consisting of n, a set of agents. I use scripts for sets, and the cardinality of this set n of agents is n, and each agent has an action set A sub I. So this is the set of actions of the ith agent, or I usually refer to it as action space. And pi I is uh, the payoff of each agent I, and that's uh, a mapping from the joint action space uh, to a real number. And lowercase a sub I is any action, and this is the joint action of all agents A1 through AN. And so for each joint action, each player or each agent I receives a payoff. So here's an example of a normal form game. This is a bimatrix game, and there are two agents, agent 1 and agent 2. So n equals 2 here, and agent 1 has actions A, B, C, and D available to it. Agent 2 has P, Q, R, S, and T available to it. One possible action for agent 1 is B, and one possible action for agent 2 is Q. So a joint action is BQ. What are the payoffs for this joint action BQ? Agent 1 is playing B and agent 2 is playing Q, so these are the payoffs. Payoff of agent 1 is 7 and payoff of agent 2 is 8. Now here's some notation that's very specific to game theory. A subscript negative I is the action space, the joint action space of all agents excluding agent I. So these are the opponent agents. Negative I is the set of all agents in N except agent I. And so this is the joint action space of the opponent agents. And lowercase a sub I is any one joint action of all the opponents of agent I. And a joint action of all agents, that is, can be written as AI, comma A negative I. This is uh, rather deviation from the standard notation, because A sub I should be here, but I've put it right at the beginning. That's acceptable notation in game theory. Now consider agent I. Given the opponent's joint action A sub negative I, how would agent I respond? Which action would agent I take? That's the best response. So the best response of agent I to the opponent's joint action A negative I is this set here, the set of all actions that would yield the maximum payoff for that agent. So it's set of actions AI such that AI equals argmax with respect to all agent I's actions of pi I AI comma A negative I. So here's an example. Suppose agent 2 plays S. Then the best response of agent 1 is this only one action D. Why is that? Because when agent 2 is playing S, we focus on this column. So agent 1 would get payoffs of 1, 5, 0, and 8 for actions A, B, C, and D. And the one with the highest payoff is action D with a payoff of 8. So 8 is the highest payoff, and there's only one action D for that payoff. So the best response of agent 1 to action S by agent 2 is D. Now, let's look at the other agent. When agent 1, let's say, chooses action B. So agent 1 is choosing action B. So agent 2's best responses are Q, R, and S. So let's look at why. Because agent 1 is playing B, we look at this row, and the payoffs of agent 2 are 2s, 8, 8, 8, and 0, and the highest of them is 8, and that corresponds to any of these three actions, Q, R, S. So this set, Q, R, S, is the best response of agent 2 to B. Now, consider another case. The best response of 1 to action R of agent 2 is C. It's this blue circle here. Why? Because if you look at the payoffs, 4 is the highest possible payoff for agent 1. Now consider best response of agent 2 to agent 1's action C. So agent 1 plays C. What will agent 2 do is look at the payoffs 5, 1, 5, 0, and 1, and the highest payoffs correspond to actions P and R. So the best response of agent 2 to C is P and R. Now you see here 4 and 5, the best responses of both agents are here. They coincide, and this is Nash equilibrium for this bimatrix game. There could be other Nash equilibria. We haven't seen that. So let's formally define pure Nash equilibrium. A pure weak Nash equilibrium is when all the agents are playing their best responses. And the actions at NE or Nash equilibrium are denoted with a superscript star. So A star is the joint action at Nash equilibrium that's equal to, for each agent I's action, A star I, and the opponent's actions, A star negative I. So mathematically restated, what we mean is all agents are playing their best responses. So for each agent I, the action at Nash equilibrium, A star I, belongs to best response of I to the opponent joint action at Nash equilibrium, A star negative I. So this is one definition of a Nash equilibrium. Here's an example. Suppose there are three agents, 1, 2, and 3. The joint action A star at Nash equilibrium is A star 1, A star 2, and A star 3. So the opponents of agent 1 are agents 2 and 3. And so A star negative 1 is A star 2, A star 3, and similarly for A star negative 2 and A star negative 3. And since each agent is playing its best response, we have A star 1 belongs to best response of 1, and A star 2 is best response of 2, and likewise for agent 3. All agents are playing their best responses. Here's an alternative definition of pure NE in terms of the payoff. No agent can increase its payoff by unilaterally switching from its Nash equilibrium action, which is A star I. In other words, if this agent I switches to another action, AI, which is not the Nash equilibrium action, then its payoff will be no greater than its Nash equilibrium payoff. So pi I AI, comma A star negative I is less than equal to pi I of A star I, comma A star negative I. Note that the switching is unilateral. So in both cases, the opponent, actually all the opponents, have the same joint action A star negative I. Replacing this less than equal to with a strictly less than, we can get the definition of a pure strict Nash equilibrium. Here's an example. This is a bimatrix game. There's a weak Nash equilibrium at CR. CR. This is a weak Nash equilibrium. Why is it weak? Because if you look at the payoff that agent 1 would get if it switched from action C to action A, its payoff would remain the same, 4 and 4. So this strict inequality wouldn't hold. That's why this is a weak Nash equilibrium. On the other hand, 3-3 is a strict Nash equilibrium. Agent 1 plays A and agent 2 plays P, and let's look at the payoff of agent 1. 3 is more than any of these, 1 and negative 4. Likewise, agent 2's payoff, 3, is also less than its other payoffs, 0, 0, and negative 2. So this is a strict Nash equilibrium.